component force system. Okay, so we do some review. The system of the object reaching a state of the rest or equilibrium is called static. So coplanar force system is two-dimension concept. As long as we can calculate the force acting on each component in the x direction and the y direction, we can apply the concept of equilibrium. So expressing in two dimensions is very easy concept. Then we can okay, let's talk about the three-dimensional force system. Reality is three-dimensional. In a two-dimensional system, force are divided into the x and the y direction. In a three-dimensional system, all forces are divided into the x, y, and z directions. So there has the three equations can be used to solve for out the three unknown. So in the two-dimensional, we use these two. In the three-dimension, we use add this equation and then solve this problem. Okay, so in this example, 450 kilonewton load is suspended from the foot shown in this figure. In the load, if the load is supported by two cables, okay, so there has a two cable and a string having a stiffness is equal to 8 kilonewton per meter. Determine the force in the cable and the strap of the spring for equilibrium. And cable AD lies in the XY plane, and the cable AC lies in the XZ plane. So we can draw the free body diagram like this. The origin we set at the point A. Set the point A. Then we have the four force. First is the loading force, and we have the the force B, FB, at the y direction, and we have the FC in the x and z plane, and we have the FD at xy plane. So we can do the equation of equilibrium. For summation fx equals to 0, we can use the FD sine 30 degree, then minus 4 divided by 5 FC, because we don't have the angle at here, so we just use this distance. We can calculate the sine, cosine, calculate cosine c. So we have equation 1. Then in summation fy equals to 0, we use the fd times cosine 30 degree, then give the minus force, and plus the FB, because of FB at y direction, so just FB equal to 0. Then summation z equals to 0, we can use the FC times the 3 divided by 5, and minus the loading force, equals to 0. So we have the three equations. Then we can use equation 3 first. We can get the FC result, and put this result into the equation 1, and we can get FD result. Then put the FD result into the equation 2, then we can get FD result. So the answer is like this. Then when we determine the structure of the spring, you know the force FB is equal to K, the stiffness, times the SAB. So we want to know the SAB. We just put the FB here, and the stiffness is equal to 8 kilonewton per meter. So we can get the SB is equal to 0.13 meter. Okay. The example, the 10 kilogram lamp here in this figure is suspended from the 3 equal lengths poles. So the poles, the length is same. So determine its smallest vertical distance. Okay, vertical distance here S from the ceiling if the force developed in any pole is not allowed to exceed 50 Newton. So the ultimate tension force at every pole is equal to 50, and A and B and C at same plane. So the tension is same. Okay, the tension is same. And you can see the dimension Fx only control at these 3 T, okay, these 3 tension force. So I think is equal to 0. Originally is equal to 0. Then use this force to calculate also equal to 0. So we just focus on the dimension Fz. Just this direction we can control this. So when we only consider the dimension Fg is equal to 0, we just use the tension force 50 Newton times the cosine gamma. We can get the z direction force. Then because we have a 3 pole, so we times the 3. Okay. Then we minus the loading force. Okay, so the loading force is equal to 10 times 9.81 Newton. Then the dimension Fz is equal to 0. We get the equation. Then we can calculate the angle. Gamma is equal to 49.163. Okay, so then we have to calculate the vertical distance S. We can use the angle and the length of the cord, and use the tension. So tension gamma equal to 600 millimeter divided by S, and we can get the S length. S is equal to 590 millimeter. This example, we need to determine the force in each cable used to support the 400 Newton react shown in this figure. So we can draw the free body diagram. We have the 1, 2, 3, 4 force. Then the loading force is equal to 400 Newton. And when we do the equation of equilibrium, we know the point D, point B, point C coordinate. So we can calculate the vector. So we can use Cartesian vector form to calculate the unit vector like this equation. So from A to B, the vector is, or you can say this is coordinate. B at minus 1.5 meter, minus 2 meter, and 4. So minus 5 here, minus 2 here, and 4. And the point C at minus 1.5 meter, and 2 and 4. So we can use Cartesian vector form to calculate. The mean is the force FB is equal to FB times unit vector. So this is vector value. Then divided by the vector distance. Okay, so if you want to calculate the vector distance, you can use the equation. Just square every number, every value, x value, y value, and c value. Then we can get this answer. Then Fc is semi-constant to do this. In FD at x direction, so just put the FD times the I part. I is vector, and the loading force at minus z direction. So we use the minus 400 Newton at k times the k. Okay, then we can summary every force together because it's static. So summary every force is equal to zero. So you can see summary everyone is equal to 0. Then we can use the summation Fx equals to 0. Just summary I part. So you can see this part, I part, plus this part, and plus this part here is equal to 0. And the summation Fy equals to 0 also J part, summary together, then equal to 0. And the Fz, I think, same complicated to do this. Okay, then we can use the equation 2, then get the relationship between the FB and the FC. So FB equal to FC, use the equation 2, we can know this. Then put this result into the equation 3, then we can get the FB and FC answer here. And then put this result into the equation 1, then you can get the FB result. example, determine the tension in each cord used to support the 100 kilogram, shown in this figure. So we the origin set point A, and we have the 1, 2, 3, 4. We have the 4 forces in this project, and the loading force is equal to 100 kilogram times 9.81, then equal to the 981 Newton. And we also have the stiffness at the spring B is equal to 1.0 Newton per meter. And we also have the coordinate D, and some angle for force C. Okay, so we can do the equation of the equilibrium. The FB at the x direction, so just FB is equal to FB times I. Then FC, we use the the angle between the FFC to x actual, y actual, and z actual. So FC is equal to FC times cosine is this cosine 120 degree I plus the FC times the cosine 135 degree J plus the FC times the cosine 60 degree K. Okay, so we can get this equation. Okay, in FD, the coordinate, or because we set the origin at A, so the coordinate is vector. So the vector like this, and we can do the FD is equal to FD times the unit vector. The unit vector is the vector value divided by the vector distance. So we can get this equation. Then the loading force is equal to 981 Newton. So in summary, every force together is equal to 0. Then we use the summation Fx, Fy, Fd is equal to 0. So the I part combined together, in summary I part is equal to 0. Then in summary J part is equal to 0. In summary K part is equal to 0. Then we can determine the relationship, or we can get a relationship between FC and FD in equation 2 first. Then put this result into the equation 3. Then we can get the FC and the FD answer first. Then put this result into the equation 1. Then we can get the FB result like this. Okay. And now we just exercise some problem. The 3 cables are used to support the 40 kilogram flower pot. Determine the force developed in each cable for equilibrium. So in this case, we set the origin at point A. We have the 4 forces. One is loading force, and FB, FC, and FD. And FB, you can see the FB parallel with the direction y. So in FC, parallel x direction x. In the D, we need to use the Cartesian vector form to do this. So the both C parallel direction x and FB parallel direction y, and the E point because we set the origin at here, so the vector is force is equal to 4 kilogram times the 9.1 Newton. Okay, so we can do the summation. I think calculate first, force first. So F E Cartesian vector form. Okay, so okay, I can calculate this here. add we can calculate equation 3 first. We can get the FD, then put the FD result into the equation 1 and equation 2, then we can get the FC and FD answer. So answer FD is equal to like this. Next exercise, I think this is a different different tool between exercise, because we can see like this exercise in the diagram origin at the point A, and we have the tangent force, so force out to the point A, and like this, also like this, and this also. But this example, you can see we have okay, the shear leg there is equal to 200 kilogram weight of the fish onto the dock. So we need to determine the compressive force. Okay, so the compressive force at A, B, and CB, at A, B, and CB, and the tension in the reaching cable EB. So the direction is different. When we put the origin at the point B, the force B is from the force direction is from A to B, not B to A. So we have some difference in this exercise. Okay, so but in this case, we have we can coordinate every point like A, C, E, and B. We can coordinate everywhere. So we just do the vector, use the Cartesian vector form, then it can very easy to calculate. The origin at the point B, the A vector is equal to x 2 and point C plus the 5.6, so 9.6, and minus 4. Okay. So vector like this, then if we can use the vector to calculate, but the force maybe show like tension because if you use a Cartesian vector form, although we set the origin at here, but the force direction is like this. How to say? If the AB is tension, the mean is force direction from B to A. So this vector I think is correct. But if the force is a compressive force, so the force direction is A to B, from A to B. So this vector maybe need to times the -1 and change the direction. So A minus R. If you use this and this, we can very easy to calculate the compressive force or tension force directly. Don't change the sign. So just do. write down the answer again. Okay. So as I mentioned, the petals just summary key part. And also this part. This part. Mention Y symbol. This is the J part. Mention FT. This and this and this. Okay, so if we can find the relationship between FA and FC first, then we can put this result into this part, then we can get the relationship like FA between FA and FD. Then we can put this relationship into the equation 3, and we can get the FD first, then get the FA and FC. Just write down the answer here. first. So I think we finished the chapter 3 here, and obviously the assignment will be announcement later. So just wait a moment. Obviously will give everyone the assignment. In chapter 3, where I will introduce the concept of the force system resultants, we focus on the moment. Okay, we focus on the moment, and now we take a maybe 15-minute break. Then we go back to the class. Okay.